So now that we have a geometry representation of our terrain, this is, regular points and primitives, a standard mesh instead of that height field volume, we can go ahead and do some extra procedural modeling on these terrain points. Now, this riverbed is looking pretty flat here. This isn't very realistic for this to be so perfectly flat, and we also want to have a bit more detail in this riverbed so that when we simulate water flowing through here, we'll have, some interesting disturbances in the water caused by uneven terrain. Now, you could apply some height field noise just in this region using some of the techniques we've already looked at, but I want to show you some geometry techniques for, procedurally modeling some of this stuff as well. So to create some noise, we can just use an attribute noise SOP. Let's connect our height field geometry results into this attribute noise, like so. By default, this is just applying color noise. So let's go to this attribute noise, change this attribute name from CD, which is color, to position P. And let's increase this amplitude a bit. And you can see when we toggle this on and off, this is kind of all pushing in one direction. And this is pushing in the positive direction in X, Y, and Z space. Now, we want to make sure that this is pushing in all directions, not just in the positive direction. So under range values, let's change that to 0 centered. And this is way too high frequency, so let's change the element size to 30. And if you want to, you could play around with perhaps using a different element size on different axes to create striations or something. So if you click this XYZ button here, this will give you per element scales. So, if you want to squish it down in Y, you could do that and maybe help to create some more of a sense of striations and your noise detail that way. And that's kind of interesting. But you'll notice that this geometry looks a little bit kind of crunchy and jagged in a way that's not very appealing. So we can fix that various ways. Let me put this on smooth shaded so it's a little bit more apparent and visible. So yeah, these sort of unsightly ridges here can be smoothed out with the Delta Mush SOP. And this is a very cool tool. This will compare our geometry in the first input to some reference geometry in the second input. And actually, this will work without second geometry being wired in. So if you just take a look at what this does without adding in the reference geometry, you can see this is smoothing out the mesh. So it's already using some logic to kind of smooth things out without relying on reference for that. But if we attach some reference geometry, then it's going to do a little bit of a better job of preserving these details since it knows, what the original position is of all the points. So if I just zoom in on this detailed area and disconnect that rest geometry, you can see it's much better once we have that connected like this. And you can control the amount of iterations that this does. So if you turn that down, this will do less smoothing. Turning it up will smooth things out more. And I don't think we need very many iterations to smooth this out. I think 3 does the job just fine. So if you look at that with and without, yeah, those few iterations of smoothing really help out a lot. Now, this is being applied everywhere on this terrain, though. We're doing some procedural modeling just in this riverbed region, but these things are being applied everywhere. So if you take a look, in a wider view, you can see this noise is being applied to the entire terrain, and the delta mush is also being applied to the entire terrain. So yeah, we don't want to mess up all of the other features while we're working on the riverbed here. So there are a few ways that we can control this. One thing we can do is on this delta mush, we can tell this to only operate in the mask region that we defined in the height field. So if we go back and look at our height field setup once again, so this is our height field, and this is where we applied a mask based on that drawn curve. Now, the height field display will automatically show the mask region in red. And, we did our processing based on that mask, but once you convert that height field to polygons, you don't see that mask area anymore. But that mask area does still exist. So, when we did our attribute cleanup, we made sure to preserve this mask attribute. And we can visualize that. You can use viewport visualizers, but I'm used to just doing this with a color sop. And if you drop in a color sop, we can set this to ramp from attribute, tell it to use the mask attribute. And here you can see this is showing us a color based on the values of the mask attribute on this polygonal geometry. So you can see, we have this nice intact attribute that we can use to limit the area that we're applying these changes to. So the mask is a value of 1 here and 0 outside with a blend in between. So on the delta mush, we can use an attribute-based ad hoc group to tell this to only process the points in that mask area. So I'll say at mask is greater than 0.01. So if we look at the delta mush once again, and maybe let's zoom in on some area that we can see both the masked region and the non-masked region, like this. If we get rid of this group that says mask is greater than 0.01, then you'll see that this region is all getting smoothed out here, and this region is smoothed out, and this is what we want to smooth. And then if we reapply this group, you can see that's limiting the smoothing to just where we want it down here. So that's helpful, but we still have all of this noise applied outside of the masked region. So there are various ways that you could address this as well. You might be able to do the same thing on the attribute noise. Like if we copy that group, let's paste that into the attribute noise. Yeah, you can see when we do that, this is only applying the noise outside of the masked area. But with the attribute noise, it kind of gives us some bad artifacts along that edge of this mask here. That looks kind of ugly. It's not really a problem when we delta mush. We don't really see any edge artifacts from doing this delta mush thing with that group, specified like so. So in this case, instead of using a group to define where the noise is going to happen, I'm going to use a custom blend shape. And this is something I do all the time when procedural modeling. Houdini has a blend shape SOP, and this has been one of my complaints for a long time, but you're unable to drive this blend shape with an attribute. So there's no way that you can use an attribute on your geometry to tell how much the blend shape is applied. This blend shape is always applied uniformly across the entire mesh. And we have a slider on this blend shape SOP, so we can just blend everything on or off. but I want to have more control over where this blend is happening. So this is something that I do very often in Vex, and that's just a pretty simple Vex code. It's only a few lines. So let's create an attribute wrangle, call this custom blend shape, and we'll connect our original geometry without the noise, and then we'll add the noise to the second input. And then inside this wrangle, we'll do a few steps. First thing is we want to get the noisy position from the second input. So I'll create a vector attribute, say vector distorted p for distorted position equals a point lookup from input 1, and we want the p attribute for position at the current point number at ptnum. And if you're not really familiar with looking up inputs in Vex, it might not be very obvious if you're not familiar with computer science stuff, but in computer science it's very common for numbering to start at 0 and not 1. So these inputs are started with input 0 here, and then this is input 1, then this is input 2, and this is input 3. 0, 1, 2, 3. It's not 1, 2, 3, 4. So when we look up point from input 1, we're actually looking up this position here. So that will give us this distorted position as a variable in our wrangle here. And then we can change our current position to match the distorted position. And a function you can use to blend between two vectors is lerp. It stands for linear interpolate. And we'll interpolate between current position and distorted p. And then we also provide a 0 to 1 value. It can actually go below 0 and above 1 to kind of overdrive this blend shape. But yeah, we're just going to stick in the 0 to 1 range for our purposes. And if we type in 0 for that third input, then that means it's just going to give us, this original position here. If we change this to 1, then that's going to give us our 0.5, gives us half of the noise. Change it to 1, we get all of the noise. Cool. So now that we're doing this blend shape in Vex, we can use the mask attribute to control where this noise blend is happening. And because we have a value of 1 for the mask here and 0 for the mask elsewhere with a blend in between, we can use that mask attribute directly to drive the blend on our blend shape. We can just put the mask value in here like so, type in @mask, and you can see now if we toggle this blend shape on and off, you can see that's using this mask attribute to tell how much to apply the noise. So that's looking pretty good, just like this. But if we want to increase, the amount of deformation where the mask is, fully a value of 1, we can add an extra multiplier on this. So let's just create another attribute that controls the blend amount. That'll be a float called blend. And I'll set that to 1.5 times the mask value. And then in this actual lerp function here, we'll change this to use the blend variable instead of the mask attribute. Now you'll notice I'm using a blend of variables that have been specified with a type and a name without using the @ symbol. And so the difference here is anytime you set up a variable without the @ symbol, that means these variables, the distorted p and the float blend, only exist within this attribute wrangle. They don't exist downstream. So, if we take this custom blend shape, put that into our Delta Mush, which will make it look a little bit nicer, like so. You know, you don't see distorted P, and you don't see blend showing up as attributes. So we refer to attributes with the @ symbol, and you know, if we were to make an attribute called blend as well, like with the @ symbol, we have to specify it differently. So f at blend adder equals blend. This will create an actual attribute because we're saying f for float type, create an attribute called blend adder. And then if you middle mouse on the Delta Mush, you can see we have this blend attribute created for us. So that's the difference between working with attributes and variables and Vex. But when you're working in Vex, you kind of have to watch out for the fact that the normals are not updated on your mesh when you change the point positions. If you use other sculpting operations, it will typically change the normals on your geometry to match. Like if we look at, I think the soft transform will illustrate this. You can see a lot of things that do modeling operations will recompute the affected normals as default. But when we're doing things in Vex, it's kind of like low-level programming to drive our effects. This is not automatically updating the normals. So whenever you're doing modeling in Vex like that, you often need to add a normal SOP afterwards in order for it to look right. So if you look at the raw output here, that's not giving us a perfect picture of what this really looks like, just looking at the blend shape directly. We need to look at this normal SOP, and this is actually giving us more of what the geometry really looks like, because we are looking at incorrect normals if we don't recreate those here. And then in the Delta Mush, this is going to do some work on the normals as well, which is why, whether we have these normals added or not, it actually kind of looks okay at the Delta Mush stage. But I'm just going to leave that on because it's safer to recreate those normals there. And then we can move on to make a couple more tweaks to our riverbed area. Now, you don't have to do these sort of changes until you start simulating the water if you want. But if you do see regions that look like they're probably going to be a little bit too low, then you might want to model those a little bit. So this particular region here, I thought this looks like it's getting a little bit too low. I want to have a higher kind of cliff edge to keep the water contained. So let's just select those points, something like that. I'm just doing this kind of haphazardly. Doesn't have to be perfect. But with some points selected in the viewport, if you tab and type in soft transform and hit enter, that will give you a transform on the selected points that has a nice fall off to the surrounding areas. Now this doesn't look very nice just yet. And actually let me reset that transform and I'll just try moving this straight upwards. This looks kind of ugly because the initial soft radius here is only a value of 0.5. Now if we start to increase this, 10 gives us a little bit of a better result, and then we can increase this a bit further, like see what 50 looks like. And 50 looks quite natural. You don't really see an obvious section getting pulled out like we did before. Let's go a little bit more extreme with pulling this up. And this is going to be really helpful to keep that water contained if there are areas where the cliff is not high enough. Now I've gone ahead and tweaked this sculpting a little bit. This is what I just showed you. And I just modeled up this area as well. So this should work a little bit more nicely to contain that water. And you'll notice that this soft transform is kind of pulling up that corner of the riverbed It's not necessarily problematic, but I want to preserve that corner that we had before. So we can use another custom blend shape. So let's delete that soft transform we don't need. Copy this custom blend shape we set up before. Paste that down here. And the first input will be the delta mush output. And then our blend input will be these two soft transforms we just made. And this custom blend shape that we set up before is applying these blend shapes only where the mask value is greater than 0. But we want just the opposite. I don't want these soft transforms to affect the areas that have a significant mask value. I only want this blend shape applied in the areas where the mask is 0, and plus maybe a little bit into the mask region. Because we have a gradient from 1 to 0 along the side of this riverbed, so I'm going to make sure that this blend shape is not applying anymore once we get to a mask value of around 0.8. And then instead of using just a multiplier on this mask value to set the blend amount, I'm going to use a fit function instead. And what this fit function will do is remap this value from one range to a new range. So we'll take a range going from 0 to a value of 0.8. So a value of 0 will become 1 in the blend. That's essentially inverting the mask. And then a mask value of 0.8 will yield a blend amount of 0. So you can see when we apply that, if we toggle our custom blend shape on and off, you can see this is really preserving this kind of corner area of the riverbed. And as I mentioned before, after we do any sort of modeling and vex in a wrangle like this, we have to reset the normals to see what that actually looks like. Looks much better. And I'll drop in a null just to label this part of the process. This is the untrimmed terrain. So now that we have this nicely modeled terrain, we can go ahead and restore that circular cutout that we had on our height field here. In the height field version, it's just based on a mask essentially, and we lost that in the conversion to polygons. So I'm just going to rename this tube for clarity. That's cutout tube. And I'm going to make a reference copy of this so that with the version that we're using to cut out the polygons, we can up-res this a little bit for a little bit nicer detail on that tube shape. So right-click that tube, go to Actions, and create reference copy. And we'll drag this reference copy down here to the bottom of our network. And with this tube, if we turn on our wireframe, you can see it's kind of low res, which might be okay, but I just want a little bit more detail around the edges. You might see it's, slightly faceted there, and I want this to be just a little bit smoother. So we have all of the parameters of this tube linked to the one that we used to cut out the height field, but I'm just going to Control-Shift-Click on the columns parameter to unlink that one. And I'm just going to increase this quite a bit to 1,000 columns for a lot more detail. And then we're going to use a couple of Boolean cuts to, carve out this circular section of the terrain, and then another Boolean to cut out the portion of the tube that we want to make up the sides of this environment. So just create a Boolean SOP, and we'll connect the terrain to the first input, and this tube into the second one. And this operation is going to be intersect. Just select that here. And this first input, the terrain, is planar geometry without thickness. So let's say treat as surface. And before we run that Boolean, I'm actually going to transform down this tube a little bit. So let's just drop in a transform SOP. Drop that in here. I'm going to shrink it a little bit just to make sure that we're slightly inset from the edges of this terrain just to be safe. Probably an optional thing, but just seems a little bit safer to me. I have a preset here for a centroid based transform. I highly recommend you create this as well. That's just going to essentially set the pivot to be based on the center of the transform's input here. And I'm just going to scale this down a little bit, like maybe 0.995, and then we can see what this Boolean intersect looks like. So we've got this nice circular cutout that matches what we were seeing on the height field, and then we can make a copy of this Boolean and do the same thing but with the inputs switched. So all the parameters can stay the same on this second Boolean, but we're just going to select that, hit Shift R to swap the inputs, and that'll give us these nice cutout sides that'll match up with this terrain cutout here. And part of the reason that I scaled down the tube a little bit was to make sure that the terrain would cut all the way through the tube instead of, things not quite intersecting at the edges. Whenever you're doing Booleans, it's really important to watch out for little imperfections like this. It might have worked fine if we didn't scale down that tube, but if you look at some of the very edges of this tube here, before we do the transform down, you can see over here, this terrain isn't quite cutting all the way through the tube. So this might cause some little issues in our Boolean cutout there. So that's just why I scaled it down a little bit, just to make these Booleans a little bit cleaner, and that gives us our end result here. Now we're basically done with our terrain generation, but this is really quite a large scale like I mentioned. It's about 1,500 units across, so I'm just going to transform this down a little bit. It's kind of an optional step, and I'm not being very scientific about real-world scales here. I'm just kind of moving this into a size range that could be slightly easier to work with. So I'll just transform this down to 0.3, and I'll make a copy of this. It's a reference copy of this ENV scale, and we're going to do the same thing to the sides of our environment, like so. And I'm also going to make sure that the environment sides have some good normals. We already kind of checked all the normals as we went along on the terrain, but I'll just make sure that's good on the sides as well. And then we can use a couple of file cache stops to save these to disk so we don't recook this whole thing every time we reopen the scene. Just make sure on these file cache stops that you've set this to save the current frame instead of some sort of default frame range. Now this terrain is pretty heavy. It's possible you might want a low-res version of this to display instead of the high-res one all the time. Perhaps your computer's getting really bogged down with lots of geometry in the viewport. It's good to have low-res visualization options sometime. So I'll just add a remesh here, and we'll connect the cache terrain to that remesh. And on the remesh, I'm going to set a larger target size of 3. So it's going to build a version of this terrain based on triangles about this size. Okay, so you can see that's much lower resolution than our original, but still gives us a pretty good representation of the surface. Now just a couple more things to finish this up. I'm just going to double check the mask values on the sides of the environment. And it looks like the environment sides have some mask values that it's inheriting from the terrain. So, the edge of the riverbed here is, generating some non-zero values of that mask on the sides of the environment. So let's just zero out the mask on there. And you could do this before or after the cache if you want. If you don't want to recache this, then you can just drop it after the cache. And in this wrangle, I'll just type @mask equals 0. And if we check the spreadsheet just to make sure that's working, bypass this, We have non-zero mask values, turn that on, and it's all zeroed out. And to finish up here, we'll cache out this low-res version of our terrain as well, and we'll just combine our terrain and the base for display purposes so that we can kind of pick and choose which of these levels of detail we want when we're viewing other parts of our scene here. And now we can move on to building some rocks and doing some nice instancing of those in the riverbed, and that'll add a lot to our environment as well.